Fifth one, current control. The torque of an induction motor can be controlled by varying the rotor current. The input current, which is readily accessible, is varied instead of the rotor current. For a fixed input current, the rotor current depends on the relative values of magnetizing and the rotor circuit impedance. This is approximated per phase equivalent circuit of an induction motor. From this, the rotor current can be found that IR equals to JXM II divided by RS plus RR by S plus J of total reactance, that is XM plus XS plus XR equals to IR at an angle theta 1. Let this be equation 66. From the equations 9 and 12, which we already discussed and seen in the previous topic, developed torque TD is given by 3R of XM I square divided by S omega S of RS plus RR by S whole square plus XM plus XS plus XR whole square. Let this be equation number 67. The starting torque at S equals to 1, TS is given by 3 RR XM II square divided by S equals to 1. So omega S RS plus RR whole square plus XM plus XS plus XR whole square. Let this be equation number 68. The slip for maximum torque is given by SM equals to plus or minus RR divided by RS square plus XM plus XS plus XR whole square under the square root. Let this be equation number 69. In real situation, the stator current through RX and XS will be constant at II. Generally, XM is much greater than XS and RS, which can be neglected for the most applications. So, neglecting the value of RS, XS, SM will become plus or minus RR by XM plus XR. That is the equation 70. And S equals to SM, the maximum torque Tm equals to 3xm square divided by 2 omega S of xm plus xr square of II square, which again equals to 3 lm square divided by 2 lm plus lr of II square. That is equation number 71. Now, from equation number 71, we can notice that the maximum torque developed on the square of the current is approximately independent of the frequency. Now, the typical torque speed characteristics are as shown here. Since xm is large as compared to the xs and xr, the starting torque is low. As the speed increases and the slip decreases, the stator voltage rises and the torque increases. The starting current is low due to the low values of flux. As Im is low, xm is large. And the rotor current compared to their rated values. The torque increases with the speed due to the increase in flux. A further increase in the speed towards the positive slope of the characteristics increases the terminal voltage beyond the rated value. The flux and the magnetizing current are also increased, thereby saturating the flux. The torque can be controlled by the stator current and slip. To keep the air gap flux constant and to avoid saturation due to the high voltage, the motor is normally operated on the negative slope of the equivalent torque speed characteristics with voltage control. The negative slope is in the unstable region and the motor must be operated in a closed loop control. At a low slip, the terminal voltage could be excessive and the flux would saturate. Due to the saturation, the torque peaking in the characteristics will be less than that as shown here. The constant current can be supplied by three-phase current source inverters. The current-fed inverter has the advantage of fault current control and the current is less sensitive to the motor parameter variations. However, they generate harmonics and torque pulsation. Two possible configurations of current fed inverter drives are as shown here, in which the first one is controlled rectifier fed current source inverter, whereas second one is chopper fed current source inverter. The inductor here, LD, acts as the current source and the controlled rectifier controls the current source in the first configuration. The input power factor of this arrangement is very low. In second configuration, the chopper controls the current source and the input power is high. This is regarding current control technique of an induction motor. If this video is useful, please like, share and subscribe. Thank you.